Sorry. Yeah, hi everyone. Today we have Chris Kymn speaking at VSA Online. I don't think Chris needs much introduction as he already been giving several talks here. But in brief, he's a PhD student at the Redwood Center for Theoretical Neuroscience at UC Berkeley, and today he's going to present us his recent work on how to combine residual number system and hyperdimensional computing. Without further ado, Chris, the floor is yours.
Great. Thank you so much, Dennis, for the introduction. And it's really a privilege to be able to speak at the VSA Online seminar again and to see some familiar and some new faces. If you have any questions in between or at any point during the talk, feel free to just comment and interrupt. But I will plan to save some time at the end for larger discussion questions as they come up. And in addition to that, I also had the privilege of presenting similar talk on earlier version of this work called Residue Locality Preserving Encodings. And I noticed that some of you were there as well. Thankfully, in the time since then, have some new kind of exciting results. So for those of you who've already seen that version, I just want to say there will be some parts that I will be going over for the sake of getting everybody kind of on the same page. And then I'll be going into some new kind of exciting applications, which I've developed quite a lot. So the work I'll be discussing today is primarily, you can find it on either this archive or this QR code, which both link to the same preprint. And this goes, the intention of this talk is to go over a lot of the information that's presented there, but kind of at a high level walkthrough of a lot of the main points. But in addition to that, I think there's some interesting kind of applications or new areas which have kind of developed or spun out since this preprint. So one is to think about how this kind of framework for encoding with high dimensional vectors can contribute to our understanding of grid cell interactions in medial entorhinal cortex. And this was a poster presented by myself at Cosine about a month ago. And then the other exciting application is to allow for better visual scene factorization with convolutional sparse coding and resonator networks, which has some overlap with the talk that I'll be discussing today. And then this paper co-authored by Sonia and myself, it will be appearing at Neuro-Inspired Computational Elements in San Diego for a full talk. So I'm happy to share more about that to anybody who's interested. And of course, this is not work that I do alone. So I want to say thank you to all of the collaborators that I've had on these various projects, to funding sources, and then to the broader community of both the Redwood Center and to the VSA community for being a really just exciting source of inspiration and motivation to talk a lot about these ideas with. So the broader question I want to start off with is how to represent numbers in order to compute efficiently with them. So as I'm sure we're all familiar with, but this is a point that we often don't appreciate, there's many different ways of encoding numbers as vectors. We could encode them as binary values. We could encode them as one hot, so 1 for one particular value and 0 everywhere else. We could encode them as base 10 numbers. We could encode them as Roman numerals. And all of these different forms of representation have different trade-offs, both in terms of how many bits you need to represent a particular number, how many components you need to represent a particular number, and how easy it is to compute with these different choices of representation. For example, with Roman numerals, it's very easy to check, for example, it's a lot harder actually with Roman numerals to multiply two numbers together without reverting to some other form of representation, but at least with binary or other base K systems, we know how to do this. And so I think an open question with all of these different kinds of systems is what can a kind of high dimensional vector framework or approach contribute to all of these different methods that we have so far? And one interesting place that I think is worth thinking at and relates a little bit to the talk we had 2 weeks ago is to look at neuroscience for inspiration in terms of understanding kinds of efficient coding principles. As we know, the brain evolved to solve many different kinds of problems, among them being the problem of how to represent one's position in space or spatial navigation. Spatial navigation, or representing one's own position, might seem like an easy kind of problem in that it's just a 2D coordinate. So at most you would need 2 kinds of neurons to represent this kind of position, or so you might think. But actually, the intriguing thing from discoveries of recordings in the medial entorhinal cortex, which is just next to the hippocampus, which encodes place cells for particular positions, are these findings of populations of grid cells, where if you put an electrode into a particular neuron and then looked at each of the spikes of where that neuron is firing as an animal is moving at particular locations, then the spikes are not occurring in random locations, but instead they're clustering in particular groups that lie along this triangular or hexagonal lattice. And there's been a lot of interesting work in computational neuroscience to characterize why is a hexagon optimal? Why use a periodic encoding as opposed to a one-hot encoding, which only encodes one particular position for every particular location? Why are these discretized scales? So why is it the case that rather than following a uniform or power law distribution over these different spacings between modules, why do they tend to be multimodal? So they cluster into multiple discrete scales that they're encoding over. And there's been a lot of interesting theoretical work that's gone over these sorts of questions. And what's come out as a result from this work in computational neuroscience are showing that the theory suggests that a reason for having these periodic codes is that they allow higher spatial resolution that's exponential in the number of neurons rather than linear in the number of neurons with one-hot or Gaussian place fields. They allow for the capacity for error correction, and they allow for parallel updates between different kinds of modules. And so while a lot of this has been worked from a kind of standpoint of ideal decoding or idealized kind of grid cells, a lot still needs to be understood about the computations between different grid modules, between different grid cells. And as we're having an increased number of recordings and ability to measure the activity of multiple cells simultaneously, we're getting better insight into mechanistic hypotheses. So this is a point that I'll come to or return to at the very end. But now I want to think about, at first, how this is going to contribute to our understanding of HD computing. And here you might be familiar or seen this broad divide between two rough clusters of representations. So on the one hand, we have these binary representations, so either 0, 1 or +1, -1 operations. In this kind of case, each component is very low dimensional. And these representations are typically used for symbolic cases or for things like analogical reasoning, where we want every particular vector to represent a discrete or different kind of symbol, versus these more continuous valued representations where every element is a phasor. So it could be a complex number with unit amplitude. But the phase can be arbitrary, and in general, it could be a continuous value. So there's an infinite number of choices. In practice, though, it often ends up being implemented with floating points. So it's a higher number of bits, but it typically represents real numbers or functions on real numbers, such as probability distributions or other kinds of kernel-based computations. The interesting thing is that this residue hyperdimensional computing framework that I'll be going over sits at an interesting point where it actually requires a lot less precision than the full continuous range of phasors, but at the same time is able to represent not just symbolic representations, but integer relations. And the nice thing about integer representations is that over a set of integers, we can have not just additive operations, but also multiplicative interactions between them. So the upshot is that it allows for the algebraic flexibility of something like the full scheme, where we have many bits per component in a much cheaper fashion, but still preserves a lot of the algebraic properties that we want when interacting with numbers, if we're willing to make the jump from real numbers to integers instead. As a sort of segue, or how to explain how we got to this starting point, I want to turn to how we generally represent complex valued vectors in holographic reduced representations in the Fourier domain, or also known as circular HRR. The starting point, or the way we can conceptualize or think of it, is first drawing a high dimensional vector. So you can think of each of these theta n's as drawn from some particular probability distribution. So these are random phases. And we have a base vector that we will call z. And then a value x, which in general could be any real value, can be represented then as a spinning of each of these phases by x. So it's simply a multiplication of this imaginary component times a particular phase, we call theta here, times x. And the way you can think about each of these representations is that each of them encodes the value of x, but with a certain periodicity or certain wraparound. And the nice thing is that if x is changed only by a small amount, then the resulting vector is going to have high similarity or high inner product with the original vector for x. So mathematically, the way we can write that or think about it is that dot products between vectors define a similarity kernel. So we can tell how similar two representations are in the original space by comparing their inner products together. And if we are, for example, using the uniform distribution to choose these phases that we're calling theta here, then the dot products between these vectors are going to follow approximately this sinc function, where the approximately is because we're using a vector of finite dimension and they're samples from a distribution, whereas within the infinite limit, they would converge exactly to the sinc kernel. And so there's a lot of work that's been very exciting that characterizes the relationship between HD computing and these kernel methods. I want to shout out from reading Tony's thesis in particular, who makes the connection to kernel methods and these holographic reduced representations very early on. And later on in 2007, I think it got a lot of traction in the machine learning community when Rahimi and Recht published this paper on random Fourier features, because it turns out that this kind of representation is a nice way of representing kernel matrices or the similarity matrix between a large number of data points in a very efficient way via this form of random projection. And then there's been a lot of theory work since, but spearheaded by like Anthony Thomas, by others in our group at Redwood, that have worked to try and characterize or understand these connections more rigorously. One kind of nice finding or that follows from thinking about this from the language of functional analysis is that the phase distribution is going to determine what the similarity kernel is going to look like. So if the phase distribution is from a uniform distribution, as we saw before, it's going to turn out to be the sinc kernel. If we pick something that's more Gaussian looking, for example, then the similarity kernel is going to look more Gaussian. And then you can play around with other kinds of shapes or probability distributions to satisfy the probability axioms, and then get a particular expected similarity kernel that will converge to a particular analytic form with infinite dimension. One particular upshot, or one kind of exciting feature of these similarity kernels, is when we consider not just phase distributions with a uniform distribution or from an infinite number of points, but we'll take into account the special case when the phase distribution is discrete. So it's sampled from the mth roots of unity. So in other words, in this case, m equals 7. And so for each of these particular vectors or values theta, we're going to sample one of these 7, each with equal probability to be the particular phase. The nice feature of this sort of periodic kernel is that now the similarity kernel is not going to be like on the previous slide where it decays to 0 for larger values, but instead it's going to repeat, in this case with a period of 7, because we picked the 7th roots of unity in this particular example. And so what this means is that in certain cases, for example, if we are trying to encode our direction or heading direction, for example, which is inherently a circular variable, then we have a way of characterizing this wraparound within the HD computing kind of framework. But in addition to that, I want to just point out that in the paper, if you read the appendix, the nice thing is that when this phasor distribution is discrete and is sampled uniformly from the mth roots of unity, you can actually derive what the analytic kernel shape is going to be. It's a little bit funky with the sines and the cosecants and cotangents, but you can actually work out what the analytic form of this particular periodic kernel is going to be in this particular case. But beyond these kind of cases where the variable is inherently circular, it remains to be seen, or it remains an open puzzle, why you would want to use a periodic kernel, or what the benefit of using it could possibly be. And remember, in the grid cell kind of case, the space boundaries that an animal might be traversing might just be an open field. It might not be something that's inherently periodic. So why would it make sense in this particular case to represent it with a periodic kernel or something that's repeating? So the argument for this, which will come in a few slides, is that actually using a periodic code and using multiple scales of that periodic code will give you a higher range or higher capacity scaling in terms of the spatial resolution that you would get than if you were to use codes which had positions locally. So then every single neuron or every single value were encoded by one position kind of uniquely. And this gives the motivation for a residue number system. Before going to that, I wanted to point out that there's a lot of interesting prior work on modular arithmetic and periodic kernels. In particular, I want to highlight this exchange between Penty and Tony Plate that's mentioned in Tony Plate's thesis, that if you think about binary spatter codes, you can think of these as a discretized version of the circular or Fourier holographic reduced representation, where it's discretized into a 1-bit or 2-state representation. And in addition to that, you can also think of the multiply, add, permute binary framework as another discretization along the unit circle. And it's worth noting that that ends up being a very special case of the phasor distribution from the nth roots of unity, where in this case, m equals 2. And the reason it's special is because, as you may have appreciated from other kinds of articles, in that kind of case, the particular inverse is going to be the self-inverse for that choice of representation. But there's a lot of other interesting work that's also thought about periodic kernels or modular arithmetic. And I hope during the discussion, we can talk more about this with people who are interested. So now I'm going to move into residue number systems and the motivations. But firstly, I want to give the mathematical foundations. So the idea is that we can represent an integer within a certain range in terms of its remainder modulo several pairwise coprime integers. As an example, if we have the number 41 and we pick our bases to be 3, 5, and 7, the reason I'm picking these numbers is because they're prime, and so then it's easy to prove that they're going to be coprime with each other. Then we can represent 41 in terms of 3 coordinates, namely 2 mod 3, 1 mod 5, and 6 mod 7. The reason we can do this is because of this result from number theory that's known as the Chinese remainder theorem, which states that if our moduli are coprime, then every number between 0 and the product of our moduli times 1, so effective range being the product of each of the individual moduli, will have a unique representation in this kind of system. So you can think of it sort of like a binary system in the sense that every bit is carrying a different piece of information, but the main difference between a binary representation and a residue number representation is that, as you are probably familiar with, in binary arithmetic or base 10 arithmetic, or then the operations require carryover operations in order to compute both addition, subtraction, or multiplication. Whereas in a residue number system, there is no carry that's required. In fact, all of the operations, so addition, multiplication, and subtraction, are element-wise, so they can be performed on each of the moduli individually without any need to perform any carryover. And then this will correspond to the same number as if we had just encoded it directly, rather than done the operations within the residue number kind of space. So the nice thing, or the take-home message here, is that these operations are very convenient from an implementation perspective because they're parallelizable. You don't need to wait for any carryover operations. And this fits very nicely with the HD computing framework of thinking about adding and binding often as component-wise operations, which can also be made very fast, parallel, and hardware-friendly. Now, to implement a residue number with a high-dimensional vector, what we can do is to pick modulo kernels for each of our moduli, and then bind all of them together. So if we have a system where we want 3, 5, and 7, for example, then we can choose our initial seed vectors or random vectors from the 7th, 5th, and 3rd roots of unity, respectively. And then our representation from each of these low-dimensional components will have range mod 105 because it implements a representation of the values from the Chinese remainder or modulo code kind of representation. So this is a quick, nice way of getting high-capacity scaling with a lot of small elements and small codebooks. And one way of appreciating why this will be nice is that, for example, if we have a residue number system with 3, 5, and 7, for example, and we wanted to store each of the patterns or the codebook elements for 0 mod 3, 1 mod 3, 2 mod 3. So there's 3 total that we need here, and then 5 total here and 7 here. In practice, we might not even need that because once we have the seed vector, we know how to generate the others. But let's just take it as a worst case scenario that we have to store all 15 of these particular patterns. Then even though we have this kind of upfront cost, we have a dynamic range of 3 times 5 times 7, which is 105. And in addition to that, if we wanted to add another moduli, say mod 11, then that requires storing 11 more patterns. So then that's 26 total. But then that represents a dynamic range of 3 times 5 times 7 times 11, or at 1155. So 11 times larger. And a nice thing, or a nice thing that can be proved mathematically, is that if you can look, you can calculate actually what the range is between the number of patterns that would be stored under this regime and what the maximal dynamic range would be. And the reason why is because it's nicely related to this problem in group theory about calculating the maximum order of an element from the group of permutations of a particular size. And because it's equivalent to that problem, you can show that its solution will also be equivalent, and that it scales as what's known as Landau's function, which is the answer to the solution, which asymptotically converges to exponential of square root and log n. So the important takeaway here is that's better scaling in terms of the number of codebooks that you store than any kind of polynomial combination will give you. And this is just a plot to show you with one modulus. This is on a linear scale, and this is on a log scale. So with one modulus, you get what you pay for. This is just logarithmically scaling. With 2, 3, 4, and 5 moduli, you get a higher effective range. But then if you want to achieve the actual bound that's given by Landau's function here, then you can simply add more moduli, and each moduli gives several orders of magnitude improvement in terms of what the effective range is going to be. So that's one, I think, kind of main takeaway, which is the large dynamic range, which is coming from using this residue number system. But the other key point, which I think is a very nice foundation, is that you can perform algebraic operations corresponding to both addition and multiplication together. So with addition, it's the same as would normally happen for Fourier holographic reduced representations, because you can think of it as a special case where the probability distribution is this discrete distribution. So in that particular case, element-wise multiplication operations between two particular vectors implement addition, because when you're multiplying two things that have been exponentiated by each other, then that corresponds to adding their arguments. So this is nothing new, and this is a nice property. And the nice thing about this operation is that the addition operations are invertible, so it is possible to unbind particular values. In addition to that, a special thing that happens when we're using the residue HD computing framework is that multiplication also becomes well-defined in terms of having inverses for multiplication, so long as we have moduli that are prime. And I'll go over the reason for this on the next slide. But the reason why this is important or interesting is because generally for phasors, or generally for other kinds of distributions, this multiplication operation would not be well defined. So it especially requires the fact that we're using these integer representations, and also that we're using moduli that would be prime. But the nice thing is that now we have two kinds of operations to perform these algebraic operations, and that they can work, or you can perform these operations within HD computing without needing to decode the value, perform the operation, and then recode the value back. So they can be done natively within this randomized vector format. And the reason for why this works, or why this is nice, is because if we take, for example, the fifth roots of unity, so I'm just showing here the different colors to map to you the different points, then we can think of these as equal to some integer value times 2 pi over n times I. So in this case, each of these numbers is going to map very nicely to one element in the group theory terms. This is the set of like integers mod 5. And the nice thing about this, I'm picking 5 intentionally because it's a prime number. And the nice thing about these prime numbers is that you can think about the finite field properties of finite fields when the numbers are prime. So what that means is that let's start with the addition case. The addition case is well defined because of the group structure between these different elements, in that each of these elements that we're going to have has a nice. So the way of reading this is to say input 1 to the binding is 0, input 2 is 0, and the output predictably is going to be 0. So this is just a way of abstractly mapping, if you have two vectors and they correspond to a particular value, what the output of that value is going to be. And in this particular case, the addition, this is the table for addition. And I want to point out that it's actually, if you look at the colors and how they're aligning with each other, it is equivalent to the colors that you would get from a circular convolution binding operation. So you can think of this as related to a compression of the tensor product in the same way that you can think of circular convolution as a compression of the outer product or tensor product more generally. So this is the group structure that allows for the additive binding operation, and I call it a binding operation because of its relationship to the outer product. But in addition to that, when we have a prime number and we calculate the field for it, you notice that if you multiply by 0, then there's no inverse for any of those particular cases. But then for each of the non-zero integers, they have a unique multiplicative inverse that corresponds to their multiplication. So if we took, for example, 2 and 2, for example, then that's going to correspond to 4. But then if we wanted to unbind and we wanted to say, how do we get from 4 to get back an original 2 representation, the multiplicative inverse of 2 is 3, because 2 times 3 is 6, and mod 5, 6 mod 5 is 1. Then that means we can take 4, multiply it by 3, and then get back 2. So this is a kind of abstract formulation of why the multiplication operation works when working with residue numbers, but I think it's nice, and it's both mathematically nice, and it allows us to perform extra operations that we might not be able to if we were working with just pure phasors. So the takeaway is that even though it might seem like it's a restrictive framework and that we're working with integers rather than real valued numbers, it actually buys us more in the sense that now multiplication operations become well-defined. So for the next part, I want to go over how to decode some of these properties and how, in particular, we can use a resonator network to efficiently perform the decoding. So if we start with the situation where we have a residue number with different moduli, and these moduli are bound together, so this is by Hadamard product or element-wise multiplication, then one kind of question comes up, which is how to recover back, if we're only given this vector zx, recover the individual factors z1, z2, and z3. One solution that could work is brute force. So manually checking all possible combinations of z1, z2, and z3 to see if they sum to or they multiply to z of x. But this is going to be very costly and not scale very well, as we want to increase the numerical range that we're computing over. So instead, we can use this technique developed by Paxton Frady and Spencer Kent in the Redwood Center a few years ago, which is developed not for this particular case, but we can use it or adapt it for our purposes. And the way that this computation works is that we try to estimate iteratively an estimate or a guess for each of these factors z1, z2, z3. So this is why it's saying z hat at a particular state t plus 1. And that estimate is based off of our guesses for the other factors if we were to unbind them from Z. So you can think of this in terms of a Hopfield network, if that's a helpful intuition for you to have, where the Hopfield networks are interconnected in terms of their states. And the aim is to come up with something that is self-consistent in terms of its solution. So when all of the factors agree, so when these factors are equivalent to Z of X, then the network settles to a fixed point solution in which it's no longer going to move. So that guarantees that it converges. And here's just an example of using it on a case where we're trying to factorize 40 from a mod 3, 5, 7 system, where you can see that it converges to the right solution, and it does so relatively quickly. As just a kind of simple example of how it converges within a finite number of iterations. And then you can check the number of iterations by seeing that the inner products are very high, and then it's also stable, so it's a fixed point. the reason why this kind of solution is nice, or why it's going to be helpful, is that it saves both space and time in terms of the amount of compute that you would need. So a standard way of checking by brute force the number of possible solutions is going to require storing 105 vectors versus a residue decoding system where we only need to store 15 vectors. And then in addition to that, notice that on every iteration of the resonator network, we're performing 15 codebook operations or 15 comparisons per iteration. So the hope then is that if the resonator is able to converge in less than 7 iterations, then it's going to save compute time relative to the brute force method, which only requires 1 iteration, but a very long one at that. So in the blue, I'm plotting how many iterations would be required just from the codebook lookup or standard approach versus the residue number system approach, where we vary the number of moduli and the number of dimensions by a certain amount. And the takeaway is that if you have an effective range that's large enough and your dimension is sufficiently high, then the number of comparisons that's required is going to beat out the codebook lookup often by an order or an order and a half of magnitude. So it's going to be a much more efficient way to recover back the original moduli than if you were to do a brute force kind of search. And so that's the nice thing, is that you have a compact codebook, so it requires less storage. And then in addition to that, it's more compact in that it saves you computation later on as well. So then to characterize the performance of how a resonator does for doing this decoding procedure, we have a few simple experiments, and I will go through these somewhat quickly because I want to go through the application sections as well. But and I also talked about some of these at the previous VSA Online seminar. But I think the key points are firstly that if you look at how the accuracy is going to scale as you pick different values or different dimensions. So in this particular case, we're saying let's increase the number of particular items that we're trying to encode. So the effective range is the product of each of the individual moduli. And then each point on this curve is trying a different set of moduli, and we're picking prime numbers just to satisfy the coprime condition very easily. Then as we increase the dimension, we see that the curve or the accuracy fall off happens at a later stage with a higher dimension. And that as we increase the vector dimension, the capacity roughly follows this quadratic fit, which is consistent with prior work studying resonator networks on bipolar or -1+1 kinds of vectors. I think an important takeaway, though, is not so much the litigating whether the fit is linear or quadratic, but noticing that for 4,000 dimensions, the approximate capacity, which just means the range in which we're able to achieve 95% better accuracy reliably with the resonator network, is in the roughly 3 million landmark. So in other words, you can encode a much higher range than the particular dimension that you're encoding. And you can retrieve it much more efficiently, as the previous slide kind of showed. So this experiment is with 2 moduli. But if you look at how the curves vary for 2, 3, 4, and 5 moduli, then you can see that the factorization problem gets harder as you add more moduli because there's more variables that are interacting with each other. And because of this, it makes it a little bit harder to converge due to this phenomena of what's called percolated noise. But even so, you can see that even though the empirical accuracy in one particular trial is taking a slight hit because you're making the problem harder, there's a massive gain in the expected range that you get as you're encoding more and more of these moduli. So even though these are plotted maybe at the same point or the same curve for the effective range, the number of codebooks required to achieve it for 5 moduli versus 2 moduli is a stark difference. So it's just to show there's no free lunch, but here's the kind of trade-off. You can have higher accuracy with less codebooks on single iterations, or you can have more numbers of moduli, and when they're segmented more, the chance of convergence on any particular iteration might be smaller, but the amount of overall computation is going to be reduced overall. And so then the last kind of thing as a check to make sure that this network is working, and then also to emphasize how the resonator network is doing in the case of noise, is to consider how this decoding capacity is changing as we increase the amount of noise that we add to the representation, and then ask the resonator to factorize or get rid of. So in this particular case, this blue curve is simply the curve in this particular case with 2 particular factors in the noiseless case. So this is just a control, and of course, it does the best than if you add noise. And then to add noise to this particular representation, because these are phasors, we add noise from a circular or von Mises distribution, where this kappa controls the concentration parameter. So more concentrated means less noise or less dispersion in terms of the phase. And you can see actually that even in this orange case, the green case for 4 and 2, this is actually quite a lot of noise being added to each of the individual components on these vectors, in that it's much larger than the range or the phasor, the distance between neighboring discrete states that can occur with the phasor particular elements. So there's a lot of noise that's being added to these representations, and yet there's a graceful degradation of how well the resonator network is able to converge, or how good its accuracy is going to be in the presence of these amounts of noise. And then in this very extreme case where it's nearly flat, it's still able to work in a very limited regime, but then it quickly kind of falls off afterwards. So maybe one kind of important point about all of these accuracy curves is that these are the accuracies within a capped number of iterations starting from a random initialization. And one point that will come up during the applications is that if we actually try to do multiple trials from different random initializations, then in this particular case, it seems, or there's empirical evidence to suggest that the accuracy over those kinds of cases is behaving or giving an independent kind of shot or probability for converging to the right kind of estimate. And so then what this proposes is a nice trade-off between the amount of compute that we need for a particular iteration and the guarantees of success on any particular one iteration, one kind of run. So this is a point that I'll return to for the two applications that are coming up. So the first application, which I'm excited to talk about, is the case of visual scene understanding. And as you've probably seen from other VSA online talks and seminars, as well as from looking at a lot of the races in literature, I think this is a really interesting kind of case where there's a lot of room to engage between some representation of particular images bound with numerical quantities like particular locations. And because there's a combinatorial search as to the space of different ways that objects can combine in multiple scenes with different colors and different positions and lightings and conditions, we need efficient kinds of algorithms to be able to efficiently solve or address this combinatorial explosion. And yet, indeed, this is what the brain is able to do all the time. The kind of combinations of images or light arrays that are hitting our particular retina at any given time might be totally new, or we might not have experienced that particular combination before. And yet we're able to still answer questions about what's in the scene, parsing out what colors or identities of particular objects are, even across a wide range of different conditions in which they can appear. So that general problem of figuring out how is the same thing across different representations is invariance. And the problem of figuring out a representation that changes or can reflect the transformation structure and along with representing the original object is something known as equivariance, for those of you who are interested. So in this particular case, what we consider is the case of taking an image, converting it, and first processing it with a convolutional sparse code to create a latent representation of this particular image. Then converting it to a high-dimensional vector. This is with the vector function architecture's representation, or simply adding up these values of particular pixel values of these convolutional sparse codes bound to particular locations. So now all of this information is now represented or distributed across this high-dimensional vector, and then feeding it to a resonator network where, in this case, we're taking simply the horizontal position, vertical position, and object identities for each of the objects in this particular visual scene. The reason why we do a convolutional sparse code in this particular case is for two reasons. So for one thing, the image or the be much sparser in terms of the convolutional sparse code, because that's what the code is optimized for. It's optimized for the statistics of a particular data set. And what that means is that for our high-dimensional vector, there's going to be less items pushed together in superposition, which means that the resonator is going to have an easier time telling these objects apart. And the second reason why a convolutional sparse code is useful is that it orthogonalizes the different patterns into different directions of the space. So this in particular is a convolutional sparse code that's averaged across the different channels or feature dimensions, but you learn basis functions when we apply this particular approach to MNIST. In this particular case, there are some loops or some curves that might look similar in terms of the pixels that they're encoding for, but yet in terms of the channel or the particular element that's being used to encode them, they're completely different. So they get mapped to different parts of the space. So that's a fancy way of saying that the convolutional sparse code helps to orthogonalize representations that are there in the original image. And the nice thing about adding convolutional sparse coding to this kind of pipeline is that in terms of the accuracy of decoding different objects, in terms of the convergence time that's required for the resonator to recover these objects, and in terms of the accuracy that's required or the accuracy that's provided when there's more digits in a particular scene. In all these kinds of cases, under fair comparison conditions, when compared to just encoding the images directly, adding this convolutional sparse code step is going to be helpful. And so then this is the work that Sonia and I are excited to present at NICE in 2024, in about a month from now. And the nice thing, no pun intended, about this sort of representation, in addition to the residue framework, is that the two benefits stack on top of each other. So if you take a convolutional sparse code and then on the one hand, use a residue, a non-residue representation where you're storing 105 different codebooks together. So then you have 105 plus 105 plus 10 different codebooks, so that's 220 codebooks. The residue number system is going to be a lot cheaper in the sense that now you only have 15 plus 15 plus 10, so in total 40 different codebooks. So that's 220 versus 50 elements that you have stored, and that's a massive savings in terms of the amount of memory that you need. But in addition to that, the number of computational operations is going to be much less as well because you're only using 40 searches per step, or 40 codebook iterations or evaluations per step as opposed to 220. So the advantage of working with the standard representation is that in these 220 searches, because you have less factors, it's going to take less total number of iterations in terms of the number of time from 0 to n. But actually, because each of those steps is much more computationally expensive, it's going to be a lot harder, or it's going to require a lot more compute to compute that solution overall. Whereas with the residue system, it's going to take, on average, longer time per iteration, but the area under the curve is still going to be smaller because you have many less codebooks. So it's a divide and conquer strategy, and it comes with a slight cost, but I think the cost is worth it, given often that the number of codebook evaluations you're going to be saving when comparing these head-to-head is going to be massive, in addition to the memory gains that you're going to be getting as well. So this leads to the second application, which is the subset sum kind of problem. And this is another case where you can use a resonator network to solve this sort of problem. So the goal or the aim is to say, you have some multiset of particular integers. Let's call this set S. And the multiset just means that a particular element could appear more than once in this set. And then you also have a target sum that's an integer that's t. And then the question is does there exist a subset of S that sums to t? In quite mild conditions, so for example, if all of the integers are positive, for example, then this problem is known to be NP hard. And so we would therefore not expect like a particular solution to break or change the time complexity of the problem per se. Nevertheless, it might still be the case that with particular kinds of optimized hardware, so there's been a lot of recent efforts to look at how to implement a resonator or other kinds of VSA architectures on neuromorphic hardware. It might be that because the resonator network allows for these kind of parallelizable operations, it is more efficient to solve this sort of problem or this kind of practical optimization problem with this kind of neuromorphic or in-memory computing hardware rather than with a conventional solver, for instance. So you can see here that if we have a resonator network and then we either have a choice of do we use a particular element or not, And remember that the search space of this is going to be the power set of S, because for every element, we have to make a choice of if we use it or not. Then in this particular case, this is just an illustrative example, the resonator is able to converge to the right solution, which is 4, 5, 10, and 2, summing up to 21. And not only does it return the answer the binary question of does their solution exist, but it provides a constructive approach as to what the values or what particular elements comprise the subset in question. And the nice thing is that if you look at the scaling of performance, the set size means that as you increase the set size by 1, the search space over this problem is doubling in size, because now you have an additional choice of if to use that element or not. And so this is a very difficult kind of problem. But nevertheless, you can see that as you increase the vector dimension from something very, very small to something 100, for example, to 1600, and then you can scale this up even to something higher, like 4096 or 10,000, then the performance is gradually increasing. But then, in addition to that, we can look at the effect of boosting our accuracy by trying multiple trials instead. So what this means is that if the resonator did not return to the right solution, and we can easily check the right solution by saying which codebooks did it use, did it say yes or no, and then sum those particular estimates up. And then either it's going to sum up to this value, in which case we have a correct solution, it's easy to verify, or we don't. And if we don't, then we can simply pick an additional random seed and then run it again. The intriguing thing is that the 10 trial accuracy curves match what we would expect from the 1 trial accuracy curves if the 1 trial accuracy were independent across particular or different iterations. So what this means is that one way of increasing the accuracy for larger set sizes is to increase the dimension, and that's going to shift our curves rightward, which is good. But a different or alternative way of doing that is simply to run more trials, so increasing the amount of compute. And that's also a sufficient way to increase the probability of returning an accurate solution later on. Now, this doesn't come for free, because if the probability in the 1 trial accuracy is close to 1%, then you need, on average, 100 trials to get the solution to converge. And then at that point, one can reasonably question if that's going to beat brute force kind of scaling. But actually, it turns out that if you take into account all the extra factors or needing to run multiple iterations or doing things again, then the expected number of iterations is, it's still scaling in a trend that looks exponential, but it's also decreasing, or the slope of this is much better compared to brute force. And in addition to that, so the constant is much better compared to brute force. But in addition to that, you're getting additional gains from increasing the dimension, even though it is the case that you're paying more in terms of per iteration because you're using a higher dimension in each of these kinds of cases. And then if we compare how this algorithm scales compared to like a CPU, for instance, or an exact solver. So the exact solver has this scaling performance where as we increase the set size, then this is on a exponential, or this is on a logarithmic scale, which means that this is going to look like a straight line, as we'd kind of expect. And actually, for the residue kind of case, for the CPU implementation, just to make this a fair comparison, we included all the time of generating different codebook vectors in addition to running the resonator network. And generating the codebook vectors in this particular case is a fairly expensive operation. It takes a bit of time to create these matrices. But nevertheless, the key point or takeaway is that even in this kind of worst case scenario where we're using a CPU, so it's not optimized for the parallel operations that we'd hope for a VSA kind of application, it still is there still is a regime in the range of like 28 or to 30 in which the residue system is able to beat the exact solver. And I think that part of this is due to the parallelism of computing a superposition from these operations. So it's not so much that it is changing the scaling or complexity per se, to be clear, but nevertheless, in this particular case, the constants do matter in many kind of practical applications. So then, with the few minutes that I have left, I want to go over not an application per se, but looping this back to neuroscience and implications for grid cell modules in the brain. So as I pointed out at the beginning, when people have looked at the recordings of several scales of different neurons and seeing how do the scalings or the distances between these different peaks cluster across different grid cells that are recorded at the same time. What the finding is that the distribution of these different scales is multimodal, which means or suggests that there's different modules. And from a residue number system perspective, this is extremely interesting because it suggests that those multiple modules could be the different modules of something like a residue kind of residue number system. And in addition to that, recently there's been a lot of work in neuroscience to characterize how a single module might wire together to continuously represent a position in space. So the kind of trademark model for this is known as a continuous attractor network that's able to integrate position updates across an environment. And a nice feature of these continuous attractor networks is that if you look at the wiring or connectivity structure of this kind of network, it forms this toroidal topology that loops around space as you would expect from these periodic encodings. But one question that is unknown is, suppose you have a continuous attractor network or a way of keeping track of space in one position, how does that update of position interact with other brain or circuit mechanisms such as place cell inputs to this network, as well as questions of how it relates to other kind of grid cell modules? And the nice thing or feature of all of this account is that the resonator network, or a modified version of it, where we're considering the input to be some transformed version of, say, a place cell input, provides a mechanistic hypothesis for how these different grid cell module architectures or pieces interact with each other. So the contribution is that residue number systems, as well as continuous attractor networks, have been well known or well studied for a long period of time. But this kind of going into HT computing and VSA and looking at the representations here, and then thinking about what algorithmic level hypotheses they provide, actually provides a contribution perhaps back to neuroscience and predictions of particular mechanisms between different grid cell modules that can be tested and looked for in the brain. And in addition to that, all the reasons for why you'd want to use this kind of system for HT computing, so the exponentially scaling capacity, and the high kind of, so the high dynamic range and the robustness and the error correction are going to scale to this sort of system as well. So to illustrate these points, I need to say, firstly, how does this work, or how does this integrate with continuous attractor networks? And how does this work in 2D? So with these points, with the hexagonal encoding of 2D space, it's easy enough to generate an encoding of 2D space where we wanted to lie on a square grid. But in a hexagonal system, what we want is both for the tiling to be hexagonal. So this is a hexagonal encoding of space mod 5, where if we go 1, 2, 3, 4, 5, then it loops around back to the same color. So the same colors plot to the same location in this 2D space, which correspond roughly to the 2D grid cell code. And an interesting or unique feature or property of this system is that you notice that if you move one in every direction, that you're actually canceling out. So actually, there's a null space in this particular frame where if you're moving an equivalent amount in every direction, you're going to end up back where you started or back to that particular position. So a way of enforcing this kind of encoding in 2D space is to, rather than pick the phases from the mth roots of unity independently for the 3 different coordinates, you're going to introduce a dependency where if the phases all sum to 0, then that is a valid distribution for the particular phases. So you can see that even in this particular case, it's a 3D distribution, but that the particular values lie along this 2D plane, and these points are in this location because of just phase wraparound. And what this allows for is a generalization of the residue number system to this 2D hexagonal coding system. And you can actually show that this is a denser packing, or provides more information than if you simply had the 1D or the 2D square lattice encoding in space. But in addition to that, you can not just by storing the integer attractor points. An intriguing finding is that actually, if you look at the inner product values of these systems, when you're not just encoding an integer point, but you're encoding something in between, it enables you to decode or interpolate these values by looking at what the 2 highest values are, or fitting this sinc function or the periodic kernel in general. And what this means is that you could actually decode 40.4 from this fixed point of the resonator network. So the intriguing or important thing is that the resonator converges to a fixed point even for these values that you didn't explicitly encode in the codebook, and that fixed point is recoverable in terms of a state in between two different vectors because it has this interpolation property, or you can recover by inverting these particular kernel values what value must have been encoded. And so the upshot of this is that you can now do path integration over a continuous period of space. Oops, sorry. Where if you have some ground truth trajectory, and then you want to use this network to update positions over space, then for a noiseless input, you're able to integrate or keep track of your position perfectly. For a noisy input, you're still able to integrate. The error is going to be a little bit off, and we quantify how this error varies for like the noiseless case versus the noisy case over multiple trials. And then in addition to that, if you're looking at the receptive fields from these different grid cell modules across a longer trajectory, so then these are the different trajectories, and then the reds are cases of particular high similarity or high activity relative to a particular item in the codebook, then they're going to represent or recreate the kind of grid cells that we started off the talk with as sort of the inspiration for. So the hope here is that not only can we take an idea, convert it to an HD computing kind of representation, and then use it for a lot of various purposes, whether these are optimization problems or visual scene factorization problems, or even just trying to express a large dynamic range in an error correcting manner. But we can also take these as hypotheses for thinking about how, if we had an idealized model of the brain, what are the mechanisms or networks that are enabling computation between different modules that allow for a high capacity kind of encoding. And so my hope is that we can not just take, brain inspiration from and add it to hyperdimensional computing, but also that we can make bridges between the kinds of algebraic operations we're thinking about with HD computing or VSA to better understand the kinds of neural computations that are happening in the brain. So this leads me to my main points, which is that for HD computing, we have this high dynamic range with low memory overhead, both in terms of bits and in terms of codebook vectors. It allows for robust error correction and a new kind of binding operation that implements multiplication. And then the broader implications are visual scene factorization, combinatorial optimization on the subset sum problem, and then this mechanistic hypothesis for computation in the medial entorhinal cortex in neuroscience. So with that, thanks so much for your attention, and happy to take any questions.
Very impressive talk, Chris. And so the floor is open for questions. Anyone who wants to start? I see Josh. Please go ahead.
Hi. Hey, Chris. Great talk. Very cool.
Josh.
Hey. So I had a quick question. I'm just curious, in selecting your factors, you have a fair bit of latitude. So you could, I just grabbed random-ish numbers. To get an M of roughly 50,000, you could have like 3 numbers that are medium 2-digit numbers, like 31, 37, and 43. Or you could have 2 that I'm not like winging this. I'm not like some sort of prime number savant. Or you could have like 2 and 3 and 8,221. Can you talk a little bit about what considerations might go into what you'd like the contours of your factors to look like? I mean, I sort of intuitively, I can imagine how you might want them to be close in size and why that might be good, but I can also maybe kind of squint and cook up some reasons why you might do it the other way.
Yeah, that's a really good question. So from the way I think about it, like one question is just, okay, when do you want to use more moduli to encode the effective range, the same effective range, or when do you want to just have 2 moduli and have them roughly be the square root of the effective range and be good or go with that? And then I think that from that kind of standpoint, the trade-off is if you have like the more moduli, then it's there's less memory overhead, but then the chance of the resonator being able to decode on a single iteration is going to be slightly lower. So that's a slight trade-off, but it's more moduli in general are going to be helpful because it is going to reduce the overall amount of computation you need to perform. But then there's a second dimension to your question, which is the like how or like when do you want the moduli to be like equally sized or like different sized? And I think there's a few ways of like thinking about that. So one thing is that if all you care about is the maximum range for a particular number of codebook elements, then I think the consequence is that you are going to have different codebook or like many different sizes of codebook elements. So as just an example of this, right? If you have a budget, say, of say like 70 codebooks or something like that, then using 2 out of the 70 to encode like the modulo 2 is going to be extremely good bang for your buck, and that it's going to double your range and it's only using what, like 2.8% of your total memory overhead versus something like 11 where it's going to take a lot more of your memory overhead, but it's going to increase things by 11. So and that kind of consideration of maximum effective range given codebook warrants using like different module or like as many moduli as possible and probably a different size. The reason why I'm trying to stick to like the same like primes of like roughly the same moduli, besides it being convenient, is that Spencer Kent in his like Resonator Networks 2 paper, when he was going over how does for the same like range or same combinatorial search, how does like the unevenness, like how uneven the size of the codebooks are affect the encoding. I think you get the best performance from the resonator when they're about of equal size. So if you use 1,010 versus 100 squared, the 1,010 is going to be a harder kind of search problem because there's a bottleneck there of 1,000 things in superposition. I mean, that's sort of the empirical result. So
Yeah, that makes sense. Cool. Thank you.
cool. Yeah, thank you.
Hey, Chris, really interesting talk. Give me a thumbs up if you can hear me.
I can hear you. Yeah.
Okay. Um, yeah, so much interesting stuff there. One question that I had was if you go to your slide 17, where you have the addition. Oh, sorry, it was yeah, the one, yeah, right, the addition and multiplication.
Mhm.
So addition in the of the angles in the phase space like corresponds to multiplication in
Mhm.
of complex numbers. And one
Yes.
thing I always wondered about with the if we try to quantize the phasors like you've done so that we just have they're basically just angles and they're quantized, then the multiple adding the angles and using a residue system works perfectly, but the superposition or pooling operation, it corresponds more to an average, and that doesn't have any clean solutions, or it often doesn't, because you there's like in here, if you took well, I guess maybe yeah. In some cases, the average doesn't end up on a point in your system exactly. And I was wondering
Right.
if, and the thing about the pooling operation, what's nice about it is that in the vector space, it gives the superposition it's similarity preserving, whereas the the adding the angles randomizes, and so a plus b is no longer similar to either a or b, which is good for binding, but you've lost
Mhm.
that similarity preserving operation. And I was wondering if you had any thoughts about the other operations that might get you something more like superposition, which is similarity preserving.
Oh, with this second or multiplication operation, how to
Well, yeah, if there's another well-defined operation here that is similarity preserving, because neither of these operations is similarity preserving.
do you mean by, oh, I see. Right, and that if you take a vector and then bind it to a different vector, then the result might not be similar to
Yeah,
either.
exactly. Yeah. So A bound with B is not similar to either A or B in general.
Right,
But when you
yes.
have superpositions, they are.
Right.
And I'm not, I don't see how to get that sort of that similarity preservation with the residue number system.
I see. So from the way I interpret it, or what I've done in just with the resonator network experiments, for example, simply doing the normal way of doing superposition, which is just component-wise addition of the phasors. It's you're completely right that this is not going to result necessarily in terms of another vector that has that might be one of these discrete phasors or moduli. I mean, the way I view or interpret this kind of problem is that even in the mod 2 kind of case, which is the -1 + 1 case, there's also this kind of odd issue that comes up, like what happens if -1 and +1 add together and then 0? Do you randomly round it together? Or you have to quantize as well. And so I think in terms of we're in the same boat with that, basically. But my short answer is that you can still add the arguments together, and it has some interpretation in terms of what you can decode from it. What I think is the harder question, and the one that I'm keen to think about or understand more, is how to find a killer application with the superposition, the addition operation, and multiplication all bound together in some interesting way. Where bound, I don't mean VSA binding, but some way to use all of them.
Yeah. Okay. Thanks.
Mhm.
Do you have more questions coming? Yeah. Technically, we are past the hour, but I guess we still have some more time if there are questions. I guess we do 1, 2, 3. Yeah.
So I've got a question. Yeah. So do your results give any indication why the grid cells in the brain have this hexagonal structure? Is it possibly something to do with, if there is an equivalent of a resonator network, the number of things that you can factorize or something like that?
Right. Here is where I would say there is a good amount of literature from the neuroscience perspective of what are the advantages from a coding theory perspective of using a hexagonal structure as opposed to a square structure. And I think some of the most compelling arguments for this come from trying to think about optimal packing arguments in terms of predicting what the optimal structure of some particular lattice in 2D or 1D or 3D space would be. And so from there, the argument then is that the hexagonal structure is the one that's going to maximize the amount of mutual Fisher information, or the tuning curves are going to be optimal when they're arranged in this hexagonal lattice, as opposed to some other kind of lattice structure that one could come up with. And then there's interesting work where people are looking at bat grid cells in 3D and trying to understand what the lattice structures are in those kinds of instances. I would say, in addition to all of that, which is nice work that a lot of other people have done, there is a reason for why from the hexagonal VSA structure or coding structure is going to give you more information in terms of space versus a square structure. So you can calculate this in terms of entropy, or you can calculate this in terms of spatial resolution, but there's a slight uptick when you use the hexagonal versus a square lattice, for example. And I think that's consistent with the findings that people found for grid cells, but I would just be wary of saying if that maps 1-to-1 onto the cortex. It's just kind of a suggestive point that's consistent with other points that others have pointed out.
Yeah. Okay, thanks.
So it looks like we're about to wrap it up. Chris, thanks again for your time, for preparing this great talk and walking us through these new ideas. And
Yeah,
yeah,
thank you so
I
much,
guess,
everyone, for attending.
yeah, thanks. And we'll see each other in 2 weeks when, as usually, Monday, 20 GMT. All right. Take care, everyone.
Thank you. Bye-bye.
I think so. Bye.